Hi, I'm Stephen Buescher, and I'm part of the team behind the AVL Simulation Suite. It's my pleasure today to introduce you to our latest release, 2026 R1. Let's take a look together at some of the highlights and new features in this release. For AEM electrolyzers, ion mass transfer between the liquid electrolyte and ionomer has been enhanced by enabling separate specification of adsorption and desorption mass transfer coefficients through the property database, while also accounting for the Donan potential as an additional driving force or resistance. Electrochemical reactions can now occur directly in the liquid phase when a liquid electrolyte is supplied, with current distribution between ionomer and liquid governed by the liquid volume fraction in the catalyst layer. With FIRE M 2026 R1, the accuracy of SOFC and SOEC simulations improves as modeling the electrochemical reaction zone was extended from a 2D surface to a full 3D volume. The model also introduces ionic conductivity in porous solids and a volumetric exchange current density. Together, these enhancements enable a more realistic simulation of the ionic transport and a better representation of how reactions are distributed throughout the electrochemical reaction zone. The mesoporous substructure model is a new catalyst layer model for PEM fuel cells. The model enables material changes, e.g., change of the carbon support material, without the necessity to recalibrate the model. Compared to the other catalyst layer models in FIRE M, the new model yields more accurate results in the high current density regime and is more sensitive to humidity variations. Porous media can now be part of fuel cell and electrolyzer models. From 2026 R1 onwards, both the porosity module and the fuel cell electrolyzer module can be activated simultaneously. This integration enables accounting for the impact of porous structures, for example in regard to pressure drop within fuel cell and electrolyzer simulations. Complex pressure drop models such as the Forchheimer model can be deployed. There is also the possibility to adjust the heat transfer between solid and fluid phases for each porosity. Furthermore, the Knudsen diffusion model can be activated for each porous domain, allowing for an accurate representation of gas transport in fine-pored materials. As an extension to the already existing multi-component diffusion model, the Knudsen diffusion effects are implemented in FIRE M 2026 R1. Knudsen diffusion occurs when the mean free path of gas molecules is comparable to or larger than the pore diameter of the material they are moving through. In this regime, molecule wall collisions dominate over molecule-molecule interactions. This is especially relevant in porous materials with nanoscale pores, such as those used in SOEC electrodes. Knudsen diffusion effects can now be enabled in addition to multi-component diffusion effects, enabling more realistic transport modeling in porous electrodes. With 2026 R1, the domain detection and potential initialization algorithm has been generalized. The algorithm now detects incorrect terminal setups and short circuits automatically, as well as cells connected in parallel or electrodes with multiple bipolar plates and GDLs. When such issues are found, the user receives a 3D visualization of the detected problem, allowing quick inspection and verification of what has been identified as incorrect. Let's have a look at a few new FIRE M features that are applicable to battery thermal runaway simulations. On the screen, you see a battery module. I select the spray module in the model tree and scroll through various result output options, including those for particle-based data, cell-based data, and pathline data. Selecting pathlines will come in handy later. In the output section, additional containers called 3D and 2D results can be found. Either of them can hold more than one selection for which results shall be written. This structure helps to organize the simulation output in our example for vented cells. In the displayed model, I have marked two face sections. They actually appear as two lines, and the names BND-arc and BND+arc are assigned to them. I'll make use of these selections when simulating arcing. Arcing causes locally high temperatures. With the hot gas, also particles are transported. Both the thermal energy and the erosive power of the particles can cause holes in the battery structure, which let the venting gas escape. Colors of isosurfaces, isolines, pathlines, and particles can represent different result quantities. In this example, the color of the particles represents the breakdown voltage. When particles move close to the bus bars, their breakdown voltage decreases. This allows us to visually identify regions with increased arcing potential directly in 3D, on a qualitative level. In addition to the arcing itself, we can also analyze particle pathlines. By activating the pathlines and coloring them by temperature, we can observe how particles gain or lose heat as they travel through the flow field. The particle traces further show different interaction behaviors. Some particles exit the battery through holes they have melted into the structure, while others are reflected back and penetrate deeper into the battery pack. When plotting the flammability index, we can clearly identify regions of elevated flammability, highlighted here in red, as well as particles acting as potential ignition sources. This combined view provides all the relevant information for an advanced battery thermal runaway analysis in FIRE M 2026 R1. IC engine development is complex, and so is CFD simulation. Today, we rely heavily on automation, for example, for selection recognition and matching setup. However, new engine designs and special concepts often go beyond what automation can handle. When this happens, automation may fail and the user is left unsure what went wrong or how to continue. That's why we have developed a new workflow. Our goal was not to replace automation, but to make it more robust by adding a safety net. We introduced a 3-level approach: fully automated workflows where possible, guided workflows where user input is required, and a manual fallback when automation reaches its limits. The new workflow is not a separate mode, but an extension of existing workflow. What you see here is a fully set up, ready-to-run engine CFD model. No matter if the case follows the automated path, a guided path, or manual fallback, the result is always the same. A simulation setup that ticks all the requirements and remains fully configurable by the user. When it comes to simulation setup, the most important information is defined first. Engine working principle, fuel and mixture, geometry and movement. The order of these steps is tailored specifically for engine CFD simulations. Automation is still the default approach. Selection recognition and meshing setup are handled automatically for well-known and standard designs. If automation cannot proceed safely, the workflow does not break. Instead, the user is guided step by step with clear inputs, checks, and requirements. The guided workflow is not a wizard that hides complexity. Key decisions are shown explicitly to the user, while low-level and repetitive tasks are handled automatically. If full manual control is needed, the user does not switch to a different mode. The original workflow remains fully accessible, with all advanced options available and full consistency. The result is a robust CFD setup process that works for both standard and special cases. Automation speeds up common tasks. Guidance helps when decisions are needed, and manual control is always available, all within a single, consistent workflow. If you would like to find out more about any of the features shown in the video today, or any of the other highlights from the release, you can check our website avl.com or look on our simulation blog. See you at the next release.